Welcome to the deep dive. Today we're really getting into something core for anyone working with large language models.
That's right.
Specifically, that massive challenge of using long context.
Yeah, the computational hit from self-attention, right? The quadratic complexity.
Exactly. And then there's the KV cache during generation. It just grows and grows.
Linearly, yeah.
Yeah.
And it eats up memory like crazy. It's a huge bottleneck.
For sure. If you're trying to push the boundaries, you hit this wall.
Which makes processing really long texts, like whole documents or long conversations, super tough.
Which brings us to today's paper. It's called KV-Distill, nearly lossless learnable context compression for LLMs.
Sounds like exactly what we need, a potential solution.
It introduces a new framework specifically for compressing that KV cache.
And the interesting thing they claim is that it creates these shorter context representations, but in a way that doesn't depend on the specific question you might ask later on.
Question independent. That's a key point, yeah. We'll definitely circle back to why that matters.
For sure. And they say it's efficient, and crucially, it keeps most of the original model's abilities intact.
Nearly lossless, as the title says. Okay, let's dig in. What's the core mechanism here?
So fundamentally, KV-Distill is a transformer compression framework. They designed it specifically for the KV cache.
Right.
The paper really lays out the problem first. Memory use scales linearly with context length, limiting how long a context you can actually use.
And they acknowledge what people have tried before this, right?
Oh, yeah. They covered the landscape, things like architectural changes to attention.
But those often hurt performance, didn't they?
They often did, yeah. Or required massive retraining. Then you had training-free methods, trying to just pick important cache entries.
How did those fare?
Kind of hit or miss, especially for this question-independent scenario. Hard to know what to keep if you don't know the question.
Makes sense.
And then there were earlier trainable compressors, but they tended to lose quite a bit of performance, especially if you tried to compress aggressively.
Okay, so that sets the stage. How does KV-Distill try to do better? What's the secret sauce?
It's a multi-part approach. First, there's a scorer component.
To do what?
To identify the tokens in the context that seem most important.
Okay.
Then they use a parameter-efficient adapter, specifically LoRA.
LoRA, okay, popular technique.
Very. And it's integrated into a slightly modified language model architecture. It conditionally tweaks the activations, the internal states, but only for those important tokens identified by the scorer.
So it focuses the changes.
Exactly. And the third big piece is the training objective. They use something different.
Right. You mentioned it wasn't the typical approach.
Yeah, instead of auto-encoding, just trying to reconstruct the original cache, they use a token-level KL type divergence loss.
Okay, break that down a bit. KL divergence.
Think of it this way. The goal is to make the compressed model predict the next word in the same way the original uncompressed model would.
Matching the probability distributions over the vocabulary.
Precisely. They want the next token predictions, given the compressed cache, to be as close as possible to the predictions given the full cache. It aligns the training with the actual generation task.
That makes intuitive sense. Predicting the next token is what these models do.
Exactly. So training the compressor to preserve that ability seems more direct than just trying to rebuild the cache itself.
Okay, tell me more about the scoring. How does it pick the important tokens?
They use a simple feed-forward network, an FFN. It looks at the token representations at a specific layer. They found layer 6 worked well, and assigns an importance score.
And then just picks the top ones.
Pretty much, yeah. Top case selection. But they need this step to be differentiable for training.
Right. The usual backpropagation requirement.
So they use a clever trick where they sort of softly decay the attention weights based on these importance scores rather than a hard cutoff. It guides the attention in the compressed model.
Interesting. And they use the same top K tokens across all the layers?
Yes, that was another finding. Using the scores from layer 6, parameter 0.6 in the paper, to select the tokens worked well across the entire model depth.
Okay, so scorer picks the tokens, then the LoRA adapter comes in. How's that structured?
It's designed for efficiency. The selected important tokens get routed to trainable query and output matrices, the WQ and WO, and attention implemented with LoRA.
Meaning only a small number of new parameters.
Exactly. They mention under 500 millB for a huge 27 billion parameter model. It's tiny compared to the base model.
And the other tokens? The ones not selected.
They just pass through the original frozen parameters of the pre-trained model. It's conditional computation.
So the model learns to adapt its processing based on which tokens were deemed important.
Right. It focuses the learning on integrating that compressed context effectively.
Let's go back to that KL divergence objective. You said it was better than autoencoding. Why again?
The authors argue that autoencoding trying to perfectly reconstruct the original KV pairs doesn't quite match how the cache is used during inference, which is for next token prediction. By minimizing the KL divergence between the next token probability distributions from the full cache and the compressed cache, they directly optimize for preserving the model's generative capabilities.
Makes sense. They mentioned using both forward and reverse KL.
Yes, with the parameter lambda usually greater than 0.5, putting a bit more weight on the forward KL.
What's the intuition there?
The forward KL helps ensure the compressed model doesn't predict something wildly improbable that the original model wouldn't have. The reverse KL encourages it to keep all the likely options open that the original model considered. It's about matching the shape of the distribution.
That's a neat balancing act.
Wow, there.
Okay, theory sounds good. How did they test it? What was the setup?
They really put it through its paces.
Yeah.
Tested on a good mix of models, LLM 27B, LLM 38B, Mistral 7B, and then the newer Gemma 2 models, both 9B and 27B.
All instruction-tuned versions.
Yep, the instruction following variants. And for the distillation training itself, they used a big mix of instruction datasets, things like self-instruct, P3, long alpaca, supernatural instructions, a diverse diet.
Good coverage. And the training details for the adapter?
They used rank-stabilized LoRA with a rank of 128, the Atom W optimizer. An interesting detail is that during training, they sampled different KV retention fractions, anywhere from keeping just 10% up to 80% of the tokens.
So the compressor learned to handle various compression levels.
Seems like it, yeah. Made it more robust.
Okay, the moment of truth. What were the results? Did it work?
Across the board, the results looked very strong. They started with that needle-in-a-haystack test.
Right, finding specific info in a long text?
Exactly.
Oh.
And KV-Distill absolutely crushed a strong baseline called H2I, which is training free. Even with 90% of the KV cache thrown away, KV-Distill maintained near perfect accuracy.
90% reduction. That's...
Wow.
Okay, what about more general QA? Like squad?
On squad, extractive QA, it was also impressive. It stayed within just a few percentage points of the original uncompressed models, even when keeping only 20-25% of the KV cache.
How did it compare to other methods there?
It consistently beat the earlier trainable methods like ICAE and DODO, and also that question-independent H2I baseline. Interestingly, it was even slightly better than H2A.
Which is question aware, right? It gets to see the question first.
Exactly. So being competitive or even slightly better there, despite being question independent, is quite something.
But there's a limit, presumably.
Oh, yeah. They noted that below about 20% retention, performance really started to drop off for all the methods. You can't compress indefinitely without loss.
Makes sense. What about actual long context tasks?
That's where it gets really interesting. On quality, a long context QA benchmark, KV-Distill kept performance very close to the uncompressed baseline, even at 10x compression.
10 times smaller cache, similar performance.
Yeah. And even at really extreme compression, like 99.9% reduction, basically throwing almost everything away, it was still way better than just random guessing.
Incredible. And summarization.
Similar story for long context abstractive summarization on Squality. Above that 20% retention threshold, KV-Distill performed as well as, or sometimes even slightly better than, the uncompressed models.
Slightly better. How's that possible?
They didn't have a definitive answer, but sometimes compression can act as a form of regularization, maybe removing noise. They did see some differences in how sharply performance dropped off at very high compression across different models, which they speculated might relate to vocabulary size differences, but it wasn't conclusive.
Okay. Did they try fine-tuning these compressed models?
Yes. On the Guberport dataset summarizing long government reports, first, zero shot, KV-Distill was comparable to the question-aware H2A and better than H2I.
Okay.
But the cool part was when they fine-tuned KV-Distill specifically on Guberport data, performance improved across all compression levels, and it held up really well even with aggressive compression.
So the compressed model can still learn and adapt to a specific domain.
Exactly. It shows the approach isn't just static compression. It integrates well with downstream fine-tuning.
This really does sound like a big step. And are they releasing the models? The compressed checkpoints?
They are, yeah. For several of the model families they tested. That's huge for the community.
Definitely. Means people can actually use this without running the whole distillation process themselves. Lower barrier to entry for using longer context more efficiently.
Absolutely. Saves a lot of compute.
Now, every paper has limitations. What did the authors flag?
Well, the initial distillation training itself is computationally intensive. That's a cost upfront.
Okay,
They also mentioned that while it worked well on the models they tested, generalization to all possible LLM architectures isn't guaranteed without testing.
fair enough.
And as we mentioned, the exact reasons for some subtle performance differences between model families post-distillation weren't fully pinned down. That's an area for future work.
Right.
And finally, the context windows of the base models they use sometimes limited how far they could push the length in experiments. But they did tease that they're working on a 128K context KV-Distill for Llama 3.1.
Ooh, okay. That'll be one to watch. And they did ablations too.
Yep, included in the appendix. They confirmed the benefits of using their KL divergence objective over simpler losses and showed that the conditional computation part, writing tokens differently, was important.
Great. Okay, we've got a solid handle on the paper itself. Let's maybe place it in the broader research landscape. How do we get here?
Well, the whole efficiency thing for transformers, especially with long sequences, has been a research focus almost since day one, right? Since attention is all you need.
Because of that quadratic scaling of attention.
Exactly. So early work focused heavily on fixing that. Sparse attention, linear attention, recurrent mechanisms, kernels, lots of different approaches.
Trying to make the core attention calculation cheaper.
Right. But many of those required pretty big changes to the model architecture, sometimes with performance trade-offs or needing full retraining.
And KV-Distill feels different, as you said. It targets the cache after attention has been calculated, more during generation.
Precisely. It's part of a newer wave, focusing on the memory bottleneck of the KV cache during decoding, not just the compute cost of encoding long contexts.
And that distinction between question-aware and question-independent methods seems really relevant here. Can you recap that?
Sure. Question-aware methods get to look at the specific query or task before deciding how to compress the context. They can tailor the compression.
Which sounds advantageous.
It can be, but KV-Distill is question-independent. It compresses the context once without knowing what questions will come later.
Which is better for?
Scenarios where you have a big document, say, and you want to ask multiple, potentially unknown questions about it later. You compress once, query many times. It's more flexible in that sense.
And KV-Distill managed to be competitive even with some question-aware methods, which is impressive given it doesn't get that hint.
Very much so. It speaks to the quality of the compression it learns.
How does it stack up against those earlier trainable compression techniques they mentioned, like ICAE or DODO?
The results in the paper suggest KV-Distill is a significant improvement, especially at higher compression ratios. It maintains performance better.
And the key reason seems to be?
They really point to the KL divergence loss. Training to match next token predictions seems much more effective for this task than the auto-encoding objectives those earlier methods often used. It just aligns better with the goal.
Okay. And compared to the training-free methods like H2 or SnapKV that just select existing KV pairs?
In the question-independent setting, KV-Distill showed much stronger performance. While training-free methods can be good, especially when they are question-aware, the ability of KV-Distill to actually learn an optimal compression seems to give it an edge when the query isn't known.
Plus, the fine-tuning aspect you mentioned. Trainable methods can adapt.
Exactly. You can fine-tune KV-Distill on specific types of documents or tasks to potentially get even better compression for that domain. Harder to do with a fixed training-free selection rule.
Okay, so wrapping up the core paper analysis, what are the absolute key takeaways people should remember about KV-Distill?
All right, number one, it's a method for nearly lossless KV cache compression, drastically cutting memory needs.
Got it.
2, it's question independent, making it versatile for contexts queried multiple times.
Okay.
3, it uses parameter efficient adapters, LoRA, so it's practical to apply to pre-trained models.
Right, doesn't require full retraining.
4, it shows strong results across various modern LLMs and sizes. 5, you can fine-tune it further on specific data for potentially even better results at high compression.
Nice.
And 6, the key technical innovations are that KL divergence training objective and the conditional computation architecture.
Excellent summary. So, thinking about the real world, what does this unlock? What are the implications?
I mean, potentially huge. Think about running capable LLMs with much longer effective contexts on devices that just don't have tons of memory.
Like phones. Edge devices.
Exactly. On-device AI that can handle more context. And for cloud providers or anyone running these models at scale.
Lower memory means lower cost, faster inference.
Pretty much. Serving models that need long context becomes way more efficient and affordable. It could make certain applications economically viable that weren't before.
What kind of applications jump out?
Anything involving long documents, definitely. Summarization, RAG over textbooks or legal files. Analyzing large code bases becomes more feasible.
Code is a good one. Lots of cross-file context needed there.
For sure. And long conversations and chatbots maintaining coherent dialogue over many turns. Research-wise, it just lets us experiment with models that can see much further back without needing a supercomputer's worth of RAM.
That scenario you mentioned, analyzing a huge document for unknown future questions, that question-independent aspect seems perfect there.
Totally. Pre-process and compress once, then query efficiently as needed.
Really powerful. Okay, this brings us to our novel notions segment. Where could this research go next? What are some future ideas building on KV-Distill?
Okay, one idea I find intriguing is dynamic compression ratios.
So not just picking one compression level, like 80% reduction, but varying it.
Exactly. Could the model learn to identify parts of the context that are like information dense versus parts that are more redundant or less critical, and then apply less compression to the dense parts and more compression to the fluffier parts, maybe based on the content itself or even how the generation is proceeding?
Like variable bitrate encoding for audio or video?
Precisely that analogy. You could imagine training a small secondary model, perhaps, to predict the optimal token retention rate on the fly for different sections.
So for a meeting transcript, compress the small talk more, keep the decisions detailed?
Something like that. It could squeeze out even more efficiency without sacrificing the really crucial bits of information.
That's a really cool idea. Okay, what's another novel notion?
Another area ripe for exploration is applying this to multimodal models.
Models that handle text and images or other data types.
Yeah. Can we extend this KV cache compression idea to handle the key value states that come from processing images or audio alongside text?
How would that work? The KV states might be quite different.
You'd need a way to score importance across modalities. Is this image patch more critical than that sentence? How do you even compare?
Tricky.
Definitely. You might need modality-specific scoring components, maybe modality-specific LoRA adapters for the compression part. But imagine processing a long textbook with diagrams and text.
Right, you want to compress the cache coming from both efficiently.
Exactly. Compressing that unified multimodal KV cache could be a huge win for those kinds of applications. It would need to build on work in multimodal attention, but focus on the compression aspect.
Figuring out the relative importance across modalities seems like the key challenge there.
For sure, but potentially very impactful if solved.
Both are fascinating directions. It really feels like KV-Distill isn't just an endpoint, but a starting point for more innovation and efficient LLMs.
I completely agree. It tackles a fundamental problem in a really effective way, and that tends to open up lots of new research questions.
Well, this has been a really insightful deep dive into KV-Distill. A big thanks for breaking it down. For everyone listening, definitely check out the paper, the links in the show notes.
Yeah, it's worth the read. And it really leaves you wondering, if we can handle context this efficiently, what fundamentally new things can we build with these models?
A great question to ponder. Thanks for tuning into the deep dive. We'll catch you next time.